Okay, so uh, today I'm not going to be, uh, this is not going to be the third installment of the Vulkan series with Rust. Um, think about this as a detour, okay? But this, I hope, will be a quick detour because I have had to explore a new, you can say, crate, which is very, very interesting for the work that, so something that I'm working on for work. So, with that context, let's quickly get started. Of course, I will continue the Vulkan series with uh, Vulkan with Rust series. Um, it's just that this one's not going to be that. All right. So today, I'm going to be exploring, or rather, talking about this crate called Pliron. It basically stands for Programming Languages Intermediate Representation. It's something that I've actually been wondering about. Uh, can we do something like this in Rust? And lo and behold, somebody's already done it. And this has been, I mean, it's got all the pieces. It's not yet fully mature, I'd say, but it's definitely got all the pieces. And it's something that I've been looking for, or rather, even me thinking about trying to do something like this for a while now. So with that context, let's quickly jump in. What is Pliron? I'll come to the design evaluation notes, but just to sort of sum it up, Pliron is basically very much akin to what's called MLIR. So if you've heard of MLIR, uh, so if you sort of, had a look at this, it's called multi-level intermediate representation. And let me just sum things up. In the past, I've talked about uh, compilers. Specifically, I've talked about things like the LLVM backend and the LLVM IR as a format. And then I've talked about how you can go from something like, let's say, where's that? Something like, which, yeah, maybe. Um, yeah, sorry. So if you remember, I've done something like this where I said, if you were to actually look at Rust's compilation pipeline, you'd see that you'd start off with something like the Rust. Let me make this bigger. The Rust source code, which is the Rust file, the .rs. That gets parsed into an abstract syntax tree. And then you have multiple levels of these IRs, what we call intermediate representations. This is where, not there, but over here, you do something called borrow checking, which is what gives Rust a lot of its uniqueness. And then there's also things like type safety and all that stuff that happens across these different kinds of IR. So this one's high level intermediate representation. This is the typed version of that. And then this is the MIR. And you might have heard, if you've been with Rust for a little while, you might have heard of things like Mary, which is MIR's interpreter. You can directly take Mary code, MIR, and then pass it on to Mary, and it's going to go ahead and check for things like undefined behavior and stuff like that. Well, you've heard of this and you've seen this in my previous streams. So Pliron is basically taking that to the next level. So basically, this entire thing that you see over here, going from HIR to THIR to MIR to LLVMIR, this is in some sense what we call lowering from one representation to the next one. All right. And then you could actually look at this if you sort of typed, I don't remember the commands, if I wanted to check cargo uh, image. Hmm. Sorry, let me see if I can try this. Cargo image MIR. Do. Okay, you wanted me to set trust flags, but there's a simpler way to do this. You can just go ahead and all right, we'll just take that one. Then let me just go, let me go, wait. Hmm. Hey, what was the command, dude? Come on. Uh, yeah, if you've noticed, I'm not using any kind of LLM, just so that you know. I screw this. I think there's a simpler way to do this. Let me, and see. Yeah, see, you can do execute this program in the Miri editor, but I don't think it's going to give me Miri. See? Yeah, it's not going to give me Miri output. Okay, I'll I'll figure it out, but I don't want to spend time on that. So basically, what you can do is you can go ahead and look at all of these different IRs, specifically MIR, to see what does it produce. Um, Likewise, Pliron is going to be a framework wherein you can basically design your own IRs depending on the domain you're working in, and then uh, progressively lower those lower from one IR, from one intermediate representation to the other, to the to another intermediate representation. And I'll sort of give you an example as well for that. But basically, the high level picture is that it's, I would effectively say it's MLIR inspired. Actually, I think the repo says that as well, wherein, um, yeah, it's an extensible compiler IR framework inspired by MLIR, but it's written purely in Rust. This was the key point that I was looking for, because when I was actually exploring MLIR, but if you not with a if you don't have a C++ background, yeah, you're not going to be able to do much with it. Uh, Anything to do with their C API or the Rust bindings to the C API, etc. The C API itself is sort of lacking in the sense that you could use the C API to sort of convert or consume MLIR and sort of maybe consume and produce MLIR type of MLIR IRs, or the in the MLIR world that's usually called an MLIR dialect. So each individual IR is basically a dialect. Uh, but yeah, so you can basically produce, you can emit, and you can consume IR and you can work with it and stuff like that. But you can't really do what's called transformations and optimizations. That's essentially what you can do with this. So when you have your code translated into an intermediate representation, the reason you want it in that intermediate representation is because you can really reason about your code and you can perform a lot of optimizations. And I will give you an example as well, one that pretty much I think the world would be very interested in right now, which is machine learning. Of course, this is not specifically limited to machine learning. This extends to multiple domains because any language that you've written, any programming language, will pretty much use this framework for optimization and then uh, produce a code that is machine code that is optimized. So that's the high level view of what we're talking about. And just to dive a little more into that so that we understand exactly what I'm talking about. So yeah, first let's talk about MLIR a bit before we get to the Pliron part. MLIR is multi-level intermediate representation. It's very descriptive. But effectively, if you take a look at the previous one that I showed you, if you saw the previous note where I said, you convert MIR to LLVM-IR, and then the LLVM backend takes over, and then you produce machine code. If you looked at LLVM-IR that we finally emit, you would see that the number of uh, opcodes in LLVM is basically around approximately 70. So if you go looking around, you'll be able to see all the list of instructions that LLVM has currently. Of course, that will keep getting extended with extensions and stuff, but in general, you can say approximately that's what you use. And then 20 or so types. Same thing for Gimple, uh, 30 with a bunch of sub ops, etc. The same thing. But the key point is both of them have a fixed set of instructions. That means you can't really extend that instruction set in the sense that unless you know, you put in a pull request to the LLVM project and they go ahead and say, yeah, let's do this because it's going to benefit the entire community. Yeah, that's fine. So when I say fixed set, I don't mean that it's, you know, sort of fixed in stone or something like that. No, just mean that it's designed to be a fixed set instruction. All right. Like you have machine architectures that can be extended with different versions, similar manner. But MLIR, on the other hand, it is not, its design is such that it's not bound to a fixed set of operations. Instructions are referred to as operations in MLIR. The whole concept over here is that the instruction set is extensible, which means, in simple words, you can say that if you are working on in some domain and you know that this particular domain has these kind of operations that you do. Machine learning is a good example. You have tensor operations. That's matrix math. That's all kinds of sine, cos, whatever you want. And there's transformations involved, a lot of stuff involved in the machine learning. Now you take another step and you go into something like cryptography. You have bit flipping and rotates and different kinds of operations that are very, very specific. You want to produce constant time code. That means um, you know, you really want to say that if you go ahead and perform an operation, that operation is constant time so that you can't have things like side channel attacks, all of that stuff. Now, so that domain, each domain has a specific set of requirements, and those requirements dictate the kind of operations that, you know, you'd want to perform in those domains. So it's a very domain specific thing. That's why MLIR is also considered a domain-specific compiler framework. So you can actually build domain-specific compilers for your domain using this, which basically means you take your code, you push it into some dialect of MLIR, and then from there on, you can pick and choose from all these other dialects how you want to like finally, you know, progressively lower and optimize and finally get your machine code at the end. The usual pathway with MLIR is that because it's a sub-project within the LLVM Foundation or whatever, it plays really well with LLVM as a backend. Um, so, so that's the most important thing. And then you can see over here, you have a lot of dialects. That is many, many different people or companies have come up with dialects that you can use to uh, work with in MLIR. Things like linalg, things like TensorFlow, things like a whole bunch of people have come up with their own dialects for their own specific. It could be their own machine learning framework. It could be their own domain. It could be whatever you want it to be, right? And thereby, the number of operations that you have access to, because the thing is, you don't have to just define your dialect and then stick within that dialect. You can, you know, mix and match stuff. That's the key part. That's why you could say that you're not just limited to your own operations. If you see something fit enough for your requirements, you can just adopt that, you know, uh, into your programs. And I'll give you an example of that. So effectively, MLIR is a collection of domain-specific languages. Uh, so you can think of that each domain-specific language is an IR that is designed to model a specific domain. And each domain, as you know, has its own set of domain-specific operations. Like you have some for machine learning, you have some for HPC, that's high performance computing, you have something for cryptography, etc. So the key thing is you can take uh, one IR that you've put together And you have this lowering mechanism, the infrastructure that's provided by the MLIR framework. You can mix and match stuff and then progressively lower your code while you're optimizing it. That means you're in the right representation to do the right optimization and then lower and keep doing that over and over till you get to your machine code. That's the idea. So you move from a higher level IR to a lower level IR that's closer to the hardware. As you do that, you're progressively trying to bring in more optimization and use it. A very good example, the reason I chose this, besides me not being a machine learning guy, is because A, it's the hot newness, and B, it's a simple example. It's very easy to understand. So there's this thing called Triton. It's a language, it's a compiler, it's a whole bunch of different things. Not important. You can basically write GPU kernels like this in Python that will eventually run on the GPU. That's the idea over here. So effectively, it's using an MLIR compiler, right? So you've written something that looks like Python. It is Python technically, but you've written something that looks like Python, and so that's something very important. Oh shit, I can't do that. Yeah, anyway, so you have to just indent that. But anyway, you've written something that looks like Python. It's not Python, but it basically leverages uh, an MLIR compiler, the based compiler, to basically produce effectively a GPU kernel that gets run on the GPU. And this is very much modeled for things like NVIDIA GPUs, because you also have similar names over there, things like block size, thread block ID, etc. So I'm not going to jump very too much into this because it's not relevant, and I want to get to the Pliron part and keep this stream as short as possible. So what's happening over here is you have this kernel. The idea of this kernel is very simple. You've got a pointer to something like an array of elements, okay? 1024 elements, maybe. And then you want to go ahead and add some value to those elements and then put that in the output pointer. And if you look at this, you would see that you first get what's called a program ID, which is in CUDA's term, this is called a thread block. It means you have many GPU threads. So a block of GPU threads can be identified by a thread block index. So you get that first. And then you multiply that by the block size. Over here, you would see that the block size is 1024. So you get the block start, and then you calculate the offset. So you can have multiple thread blocks. Because of that, you can identify which thread block and which thread in that thread block. That's what the offsets is dealing with. And then you load the values uh, in that thread block for those threads. You load the values at that into the value X, and then you basically do X plus Y, and then put that in the output. Uh, then this X and Y, this output is in memory somewhere. And then you do the store over here. This thing's supposed to be like that. So, and then you store that to the output pointer. Same thing. You add the offsets to the output pointer and then you store it. And this is, as I said, one of the many IRs that is produced. So this code goes through an intermediate translation, which looks like this. It's called TTIR over here, which is Triton IR, right? It's one of the many MLIR DSLs or dialects you can think of. And it pretty much has a one-to-one mapping at this point. Of course, when you optimize it, it won't. But it pretty much has a one-to-one mapping. If you see over here, let's take a look at the first one. You say that the block size is a constant. That's what const expression is trying to say. And that constant is about 1024. You put that value in this person. So all variables are marked with a percent symbol. And then you have program ID, which is the same thing. Again, close that. You put that in person 0, which is whatever thread block ID we're talking about. And then edit. As you can see over here, this is not an operation from the from TTIR, which is the Triton IR. This is a dialect that was separately probably maintained by, it's actually So I'm correct. It is part of the MLIR standard library, maybe. I don't know if you call it standard library, but standard dialect, maybe. And you're using one of them. You're not using just TT. You're not just limited to what you want in your domain. You can just make use of stuff from elsewhere. So you do the multiplication over here, and then you make a range, which is what you see here. To calculate the offsets, you multiply that with the block start. The interesting thing that you'll see over here is you'll see this. Sorry, let's start with this because this pattern repeats throughout the code. Splat is basically you take a scalar value and then you create a tensor and you repeatedly, so you initialize a tensor with the same value across the tensor. So if you create a tensor of 1024 values, basically a vector, you want to initialize that with the same repeated value for all those 1024 places. That's what Splat does. And then once you do that, then you go ahead and do the addition to create the offsets. Like this, the entire IR sort of maps one to one. And now you're in this space where you're producing these immutable variables called SSA variables. And you have a lot more type information, a lot more clarity around how your code is being structured and organized. Which leads us to say, what's the point of all of this? Here's an example. You can go ahead and do something like this. So you see that over here, I think that's what I put here. So if you see here, %8 and %9, you're doing something called a splat, and then you're adding, whatever you're talking about. So the splat is the broadcast, but you basically take a scalar value f32, and then you create a tensor with that f32 value repeated for 1024 times. That's what this thing does. And if you take a look at 7, it is loading all of the values at this pointer. So, in this tensor, it contains a list of pointers, 1024 pointers. It's going to load those values at those memory addresses into another tensor, and basically that's number 7. So you take this tensor that you splatted, and you take the previous tensor that's got all the pointers in it and all the values, and then you basically do the addition. Then you'll obviously get another tensor. Now, this is the double operation. You're first plotting, that means you're first creating a tensor with the same repeated value, and then you're adding it with another tensor. All right. Can we do better than this? Rather than tensor operations, can we just do, you already have the scalar, why don't you just add it to the tensor, right? Can we do that? Yeah, that's what you can do. You can create your own dialect, and you can have this operation in there, which is your custom operation, says, okay, I'll directly add a scalar in a vector or a scalar in a tensor over here. That's what I want to do, all right? And that's kind of what I'm saying over here. The reason you would do this is because some hardware architectures actually support this operation, which means you're executing fewer instructions, which means if you had a large number of similar kinds of operations, you're going to be an order of magnitude faster. That's your performance. And then you're also not doing a lot of stuff, which is platting and rematerializing and all that stuff. You're not doing all of that, basically. So that's effectively what you get with MLIR, right? Now, if you sort of, and this is what I explained in the example, so you can simply write a pass that changes your IR so that you add this optimization in there and basically get support for vector scalar operations, which was not there in the previous IR. So with that, if this is basically what MLIR can do for you. Now, the biggest problem with MLIR, at least for me, was the fact that it's written in C++, and it's very much tied to LLVM, and there's a whole bunch of things that don't work for me because pretty much we've been trying to build a Rust toolchain end to end, and it gets really weird when you're trying to work with something like C++ in MLIR with LLVM and then some Rust components in between. We'll talk about that maybe some other time, what the problems are. But effectively, Pliron is the same thing as MLIR, but it's purely written in Rust, which means you can do all these, uh, you can generate, or you can create your own dialects and your own operations and your own types and stuff, and then you can progressively lower them just like MLIR, right? But the fact that it's completely written in Rust, it's very good. So the first thing I did is actually jump into it to understand, you know, how the crate works. And it's great. The first thing you should say is, as I mentioned, the IR format is very similar, except for the way I think the way it's printed out. So if you see the thing, it sort of looks like this. Uh, MLIR also has this generic format view. By the way, this view that you saw, wait, where's that? This view is not the MLIR actual view because this is formatted. So you can do own custom formats and stuff, just so that you know. Anyway, so Pliron has a very similar IR format that it uses like MLIR. It is SSA based, and it has this thing called a recursive nested structure, um, which means if you look at the IR over here, you'll see that this built in is a dialect. You can think of it that way. Module is actually an operation, right? And this is like the name of the operation. Within that, you can have regions. And within regions, you can have blocks. That's effectively how you would look at MLIR. So because I've got notes over here, I'll just show you that as well. So you'll have operations. Within operations, you'll have regions, and within regions, you'll have block. And this is the full syntax of a typical MLIR instruction or operation. You'd see that it has the result, which is starts with the person symbol, the dialect, the operation name, the actual argument that it takes, and any compile time constants that you want to give it. And then the types of the arguments. So this is the input and it produces the output. This is the input type and this is the output type. And then there's a location. All of this stuff is exactly present over there, but you just don't see it in the same format. So, right? So yeah, that's one. Then interesting enough, uh, like we discussed in things like the crane lift compiler, etc., where crane lift uses a very unique way to store its entities. That means whatever is part of the crane lift IR. So crane lift has its own IR like LLVM, and there's its own opcodes and stuff. And then you can basically go ahead and look. If you look at the crane lift IR, you'll be able to see that it's got its own opcodes, it's got its own stuff in there. And the way it actually works is it works with what are called entity references, etc. It's a very similar concept to arenas, which I will talk about. The fact that arenas, the way Pliron uses it, is they use the author uses a crate called slot map, which is basically generational arenas, wherein you are not just going to be talking about um, indexing into your. Okay, I'll just talk about that. Let's just say that there's something called generational arenas that exist over here, and it's used for really efficient storage and access. That's what, because in the IR, you'll have the regions, you'll have the operations, you'll have the blocks, and you'll have, again, the operations and stuff. You want to store this stuff, these operations, very efficiently because there's going to be a lot of them. And you want to be able to reference them. You want to be able to gather information about them. You want to be able to query them. When you want to do all that, you need to have them in a very good, you know, you need to neatly organize them. And that's what generational arena does. Then comes the other part, which is macros. This crate leverages quite a bit of macros. Only concern is with this, I mean, I understand why it's being done, because in MLIR, you'd use something like table gen, which is a DSL, just like how crane lift uses its own DSL. I guess in Pliron, that's not required. I believe so. I think the author talks about that. But with macros, as usual, it does impact readability and maintainability. But as I always say, there's always a workaround that, and I will show you that as well. Yeah. And then there's extensibility. This is the part that MLIR really had, did really well. That means how do you make the IR extensible? That's the whole point, right? How do you really, let something like AIR work with BIR? How can you do that? You got to have some glue stuff somewhere and make things work. Well, fancy stuff. It's just interfaces, or in Rust, it's traits. That's about it. But there's some amount of gluing that needs to go on to say, okay, can we take this type and sort of convert it into that? And can we, if we get this type, can we sort of query it uh, at runtime? Things like that tend to become a little more involved. And that's what extensibility is all about. Additionally, all of the stuff that you don't have to deal with when you go to C++, uh, or the C API for MLIR, same thing is not present over here because it's completely written in safe Rust. So you get the type safety, you get the borrow checking, you get all that stuff, and it's really, really easy to work with. For example, with MLIR, it's the LLVM ecosystem. So getting the build system up, putting that together, understanding the damn errors are like, dude, I need to have years of C++ under my belt, like really figure this out and be really productive in it. And yeah, that's the thing about a language. If you invest in it, um, it should technically make things for you easier. And guess what? I just came across this great, I don't know, seriously, just about a day or 2 days ago. And I managed to like put some pieces together in my head and become a little more confident in, taking it to the next level. I'm not talking about the next level because I don't think I can talk about it, but just so that you know that this is a very key part. Making something like this accessible is very, very important so that you can have a lot more people who may not have a compiler background easily get into something like this. Right. And then I already mentioned that there are dialects. So the dialects over here are Pliron has so there's already an LLVM dialect that's implemented in Pliron. And I'll show you that as well. All right. So that's the context. Um, and today I'm not basically going to jump right in and show you, uh, like I've not written an IR in Pliron yet. Just put together some pieces. I'm not going to be discussing them right now, but I'm just going to go through the crate, sort of talk about how it's laid out and stuff. This is mostly going to be um, sort of for me, because when I do come back come back from the future, come back from the future, uh, I need something to go back and look at so that I know exactly what I learned. And also, if it helps anyone, this is for you. All right. So in Pliron, you have some core data structures. Lo and behold, those data structures are not very different. They are uh, operations, attributes, and process, very similar to what you'd find on in the MLIR space. I'll talk about the context, then we'll go a little bit into the generational arenas. At least I'll show you some stuff that I've put together. Um, yeah, and then we'll sort of look at the extensibility part as well. There's some def use chains, etc. Anyway, let me see if I can, because all of this is going to be me just exploring the crate. Not really sure how useful it's going to be to someone else, but at least the first part gives you an idea of what you can do with this. All right, so let's quickly jump into, the first thing, what we call generational arenas, because I'll be talking about all of this with something like generational arenas. Sorry, for example, the operations and the types and all of that stuff. When you do create them, when they're part of your IR, they need to live somewhere. So there's this thing called arenas. Arena is basically a fancy term. You basically get a chunk of memory, and then you're responsible for managing it, right? And then you add this other term on top of that called generational arenas, wherein you're basically saying, you know, um, I want this really cool data structure where I only use a vec, but when after that, yeah, if there's an element in the vec that's already occupied, that means I've already put something into one of the elements in the vec. I need to go ahead and ensure that I check to see whether that element has ever been reused or whether that slot in the vector has been reused. The reason you want to do this is because, if you try to do something like, each operation, I'll have it somewhere in memory, then I'll have a bunch of references to it, etc. That's going to be very difficult in Rust because the borrow check is going to kick in and say, ooh, sorry, can't do all of this stuff, right? So there's a little different way of doing things in, uh, I think it's very much in the compiler space, you have this thing. Because even when you looked at the Grainlift compiler as well, I talked about entities and entity references. The same concept. You really don't have like a hash map and then you have, and that stores the key and the value. You just have a vec, so you have a more condensed storage. And the keys are computed for each slot. And then you use those keys to sort of, index and get the value and do whatever you want with it. So that's a key point, right? The keys are not part of your storage itself. They're actually present during, present. They're available to you whenever you insert an element into one of these vectors. You will be able to retrieve the key that is associated with that, and then you can use that at any other point in time to retrieve the value as well. All right, I think that's confusing if you just listen to me yap off the bat. But let me show you a picture of this. So I put something like this together. So the way this works is you have a particular kind of storage for operations, for regions, for basic blocks, not slots. And uh, you'll see that this is so this is element one in that operation vector. Usually all of these things are vectors. Slot 0, slot 1, slot 2, slot 3. And then the data piece is whatever the data that you want to store in there, which in this case is going to be an operation. I should put that in there, but fine. And then you also have a field that says whether it's occupied or not. This is a U32. And then you can, if there's a slot that's free, so this data field is actually what you call a union. It's like an enum. It's an untagged enum, you can say, which is a union. And you'd be able to figure out what the next free slot is. So slot 3, it points to slot 3, so slot 3 is the next free one. And this slot is part of the head list. Okay, I'm not going to sort of confuse myself as well, but just know that it's a data structure that is used to store things like operations, regions, and blocks. And it serves as a central storage, as I put it over here. And this includes operations, regions, and blocks. The thing that you need to know is that we use these index types, sort of index into, this vector. Okay, so it's not like a standard index. The index has more than just the usual index value that you look for, which is 0, 1, 2, 3. It also has something called the version. This version is the generational version. So if you ever go to reuse the slot, you know that you can check the version here and the version in here and to see if they are the same thing, then I can probably return it. If they're not, then something went wrong. You should just throw an error. Okay. So with something like a generational arena, you would be able to produce this data structure that's very cache friendly, number one. Number two, it's very dense. In fact, that it's just a vector and you keep reusing slots in there so you don't take up too much space. That makes it dense. And it's just, very efficient to do things like this when you're working with compilers. So yeah, that's the first thing. But where do all these operations, regions, and blocks live? Well, in a compilation, if you're trying to compile something, they live in something called the context. Usually that's the case. You put your operations, your basic blocks, and your regions in some other type of metadata in there. Not going to go over them. And then this stuff is put in an arena cell. Arena cell is nothing but a slot map, which I already mentioned. A slot map is like a hash map, but without, if you look at this, just look at the type over here, and you will see that there is there's no key in there. I mean, the struct has no key. Uh, the key is just part of the phantom data type, right? So you need that when you're expressing the type, because you want to make sure that the compiler keeps that in mind. But you don't uh, really include that. So the in-memory representation will never have a key. That's what I meant to say. And then, as I mentioned, the whole thing works as expected, right? So you're able to go ahead and query the slot map, the values in the slot map using, generational keys, and then retrieve the data that you want. All right. Pliron, again, here's where you can say Pliron uses slot map. So slot map provides a nice little helper macro called new key type, which means if you want to turn something into a key, you can just basically say arena index new key type. It this is the macro, it expands to this. And a little more than that with some traits, etc. Right? And you take whatever the arena index is and you put it inside this type called the pointer. That's why this is the index. That indexes into a generational arena, right? Quite simple. Okay, so that's one. And then I think the last thing that I want to sort of discuss, because it's sort of very interesting to me, is there's quite a bit of what you'd call dynamic typecasting going on over here, which you often don't see in a lot of crates, or it's rather hidden in many different crates. But yeah, great. Um this one has it. This one has a lot of macro usage, and there's very specific reasons for that, I believe. So here's an example. There's a type called trait casters. So as the name sort of implies, you're trying to cast something to a trait, right? So let me just explain this very simply. You're going to be given two types, or rather, two things. One is a type, and the other one's a trait. And then you're going to be given a closure or a function pointer of some sort, which is boxed up. And you want to ensure that can I use that function to take this type, the type one, and cast that to type two, right? The reason you want all of this done and you just don't want to like implement it with traits, etc., is because you want to do all of this at runtime. And that's pretty much what you're going to be doing. And then you have there's a trait. You want to, so there's this thing called the distributed slice over here, which is, this has nothing to do with Pliron. It's a different crate called link me. So you can have something like this, a static global, and you can define your own type in there. And then elsewhere, when you want to add something to this array, you can go ahead and keep defining your own trait caster that will get added to this slice. It does some link time magic, so to sort of work with that. That's just implementation detail. But effectively, you see a lot of this, all right? The reason this is kind of important is because, let me see if I can show you an example. Yeah, I think I have one here. So see, so what happens is you want to take a type and check it whether it can be cast to this trait. And you come across this a lot in something like MLIR or Pliron kind of a thing, where you're not particularly only talking about the Rust type, you're actually talking about the types that you have defined for your IR. You want to see whether these types can convert to some other type that you have, and you want to make these, and you don't have enough information to make that call at compile time, but you want to do that at runtime. Here's the option to do it. Yeah, but when you start looking at things, there's a lot of macros involved, and you'd be like, whoa. Uh, but I don't think the macros are too heavy as well. Unlike, let's say, You looked at some web framework, for example, Axiom, you'll be like, my God, you invented a whole new language, a whole new way of basically writing, Rust. That's what it feels like. They probably need it, probably don't. I don't know. But this is relatively simpler. And I think that's okay. But the only thing is, once you start opening it up to a lot of macro usage, what happens in the long run? Question. All right. So here's what's happening over here. You can, so there's a macro over there that says type to trait. You give it a type and a trait. It's going to try and see whether at runtime you can basically cast this type to this trait. As simple as that. And there's the infrastructure required for all of that is already built in to uh, Pliron, right? And you'd be able to see that over here. So this is the context. I've just taken a few notes from over there. And you'll be able, this should be pretty straightforward. Yeah, one thing I wanted to mention is if you went ahead and tried to sort of go through all of these, what you call, if you try to expand your Pliron crate, you'll be like, I am not going to go through and sit and figure out what each proc macro does, because a lot of the stuff is actually derived macros or attribute macros, etc., implemented as procedural macros. The best thing I would say is just go ahead and expand them. And once you do expand them, you can go ahead and simply look at the expanded version, and then you'd be able to do. This is something that I've talked about quite a bit. I will always repeat it because it's better to just go look at what is produced rather than go read the macro. Because implementations can get really hairy when you get into it. Anyway, so that's Pliron. A very quick, high-level glance at things as to how things are working with Pliron. And I believe what I wanted to show you was where is that? Yeah. So this is where your proc macros live. Um, it's not too much of work. So far I've talked about some of the nitty-gritty details of Pliron, but I've not talked to you about like how do you actually define your IR and how do you make your ops? So what is your IR? Your IR is made up of things like ops, types, your own ops, your own types, your own attributes, whatever, right? So the way that works is you define your operations. For that, you just use a proc macro on top of a unit struct, and then you magically have your operation. And then you go ahead, create your types in a similar fashion. You go ahead, create your interfaces in a similar fashion. Sorry, attributes in a similar fashion. And then you can also have those ops implement these interfaces so that they can expose a bunch of properties. So let me explain that because that's a good way of looking at things. Um, Let me start with yeah. So I mentioned there's an LLVM. So there's a version of the LLVM IR dialect in Pliron. That's why you'd call it Pliron LLVM. It's not LLVM IR. You take LLVM IR and you give it to Pliron, and it should be able to produce Pliron, the LLVM IR, do your own thing in there, and then again convert that back to LLVM IR. That's what you can do with this particular crate over here, which is a sub crate. So you can look at that, or you can simply go ahead and look at the built-in. So built-in is something like, let me just show you what that looks like. So if you go and look at the operations in the built-in dialect, which is the standard dialect, you can see that, yeah. So if you see this over here, there's something called function op, okay? Everything is an operation, including a function. It's also an operation. Just like in Rust, a function is basically just another type. In Pliron or in MLIR and Pliron, etc., A function is just another op. So what happens is you create your own op. This is how you write your op. And then you annotate that with two procedural macros. It's as simple as that. No table genning, nothing like that. In the sense, no separate domain-specific language. Like in LLVM, you have table gen. Crane lift, you have something like, I forgot that, ISLE. It's called instruction selection and lowering expressions. It's not that that they're bad or something like that, just saying that they're there for very specific purposes, maybe. And here, it's much simpler. You just use a procedural macro. So what happens when you actually do this? Um, One is I just go to the expanded lib and look at something like pub struct funk op. Funk op. So when you see that, sorry, uh, you will see that when that macro expands, you will see that it actually creates. It's actually a wrapper around this pointer to an operation. That's what it holds. And as you know, the pointer to the operation from what you saw previously is basically pointing to some operation in a slot in the generational arena storage, right? That's about it. And this stuff, you see one region interface, all of these are the interfaces that you are saying you want to implement. What does that mean? So if I just go back, sorry, where was I? Yeah, sorry. So if I just go back, you'll see that there's another proc macro that says derive op interface implementation. So let me take the first one. The first one is define op. So define op, if you want to go look at it, here's the full proc macro implementation. So if I've called defined op, I'm basically going to go ahead and end up over here, and it's going to call this function, and it's going to parse the what you would call, yeah, let me just run from here. Yeah. So it's going to call two token stream, which is this, and it's going to say derive op, def op, whatever. So you will be able to see that the name of this dialect, which is built in, and the operation within that is the first thing that's consumed. So if you see this, I'm sorry, you see this, you'll see that we first parse the name into a string literal, and then whatever follows that is the pub struct thing, goes into input, and then you create your def op. This is how you create the operation. Simple as that. At the bottom, you'll see somewhere that you're creating a proc macro. Where is that? Oh, sorry. So you create a def op, and then you say, just convert this into a token stream. And then, yeah, here's where you do that. Finally, with all that, you'll end up implementing this two tokens straight. This is regardless if you work in Pliron, this is just procedural macro stuff. You will be able to produce this, which is, as you can see over here, this is exactly what's produced in the expanded output. This is exactly what's produced in the expanded output, right? So same thing over here. Not a lot of difference. So that's how you can pretty much create your op. And then you also define this op trait because it's an op. So you'll be implementing all of this stuff as well. So if I just go back to the expanded output and then scroll way all the way to the bottom, because all of these are trait implementations that come afterwards. And yeah, you'll be able to see the implementation here. Right. So this is one of the things I always say, just expand the macro, go ahead and look at the implementation. It'll just make things a lot more easier than you having to sit and sort through everything. Likewise, you'll be doing the same thing, the op. So whatever you saw over there, if you went ahead and looked at this, one region interface, isolated from above, symbol op interface, all of that stuff is also, if you go look at the derive or the macro, sorry, where is that, man? If you go and look at this interfaces.rs, you will see that it's all implemented over here, right? I'm not going to walk through this, it's going to take a while. Uh, but yes, that's exactly how you go ahead and define for something like your built-in module. Yeah, for built-in module, for a function op, you would be able to go ahead and define the operation, and you'll be able to go ahead and define the operation interfaces that you want. Basically expose the kind of operations that this particular operation will provide, the properties of the operation. For example, so any op that implements this one region interface, it basically says that operation only has one region. And any op that defines a symbol or declares a symbol, you will have this isolated from above. The fact that the documentation is pretty good should tell you everything about the crate. So the idea is, so far I was wondering how much work would go into creating something like the MLIR framework. Well, as you can see, there's a certain amount of effort, not too much, but it's already done. It's already done. That's the best part about it. You just have to build on top of this. Maybe say you want to build something similar for Pliron LLVM. You have Pliron crane lift. Yeah. So, and then you can have other IRs, which I will talk about when I do get to that part. Um, so you can create your own IRs, and then you can progressively lower them, doing your optimizations for your specific targets, right? This is a very good. I was really thinking about something like this, and see, it's 95. It's 100% pure safe Rust. And I presume the author, I have watched, I believe, one of his talks as well, which is very rare. Somebody actually put it out. Um, I believe this is something that, and he talks about the same kinds of problems that he faced when he was working with C++. Although he's a compiler engineer who has considerable amount of exposure or time spent with things like LLVM as well as MLIR, um, I believe he's working in the Rust space on some crypto kind of a thing. Um, and he's been trying to figure out how do I make these things sort of MLIR work with Rust. And he tried with the C API like I did, or like many people did. It didn't get you very far. And the LLVM maintainers are also were not really helpful in terms of trying to say, can we merge something like this, so that it wouldn't get a lot of support for that, I believe. So he went ahead and wrote his own thing. That's open source. Lovely. So I'm really glad I found this, and I really wanted to put this together quickly, put my thoughts together so that I can come back to this in the future and uh, really see if I can. I am really, really interested in contributing to this. But yes, so that is MLIR and pure Rust. Now it's called Pliron. Yeah, I would say one thing. Maybe some of these names, like the type names, etc., could use better names. Or maybe I'm wrong. I don't know. We'll figure it out. But yeah, it's was great for me going through all of this for a couple of hours now. All right, so I think that's about what I wanted to cover, because I don't want to like bore everyone with all the nitty-gritty details. But I guess that should provide a good overview of what Pliron is and how it's very useful in the Rust ecosystem. Okay, that's about it from my end, and have a good day.